Today we're going to be studying more about stresses, and in particular we're going to be studying what's called stresses on inclined sections. This will move us one step closer to our full kind of theoretical understanding of what's called plane stress. And it's kind of a practical way to kind of understand what's going to happen later. So this is more kind of an intermediate step to kind of ease the transition to a more general scenario for stress. So if you recall from prior discussions, when we introduced the idea of normal stress, we took a bar, and that bar had to be prismatic, had to have homogeneous and isotropic material properties, and then we would cut the bar along a vertical plane, and then we would look along this cross section, right, and we would call this the normal stress, okay, which is force per area. Okay. Now, what we realized is if we had this scenario where you had a bar, and it satisfied all those assumptions with the loading and the geometry and so forth, that if you took a perfectly vertical cut, that this stress sigma would be constant, right? It would be evenly or uniformly distributed over this area, right? Over the cut where we make the cut. And if you took this distributed load and created a resultant force, it should be equal to P. Okay, so there's a balance between external and internal forces. Okay, now today what we're going to talk about is, rather than restricting ourselves to these vertical cuts, what if I take a cut along some other angle, right? Any angle that you want. And then I want to study the stress on an inclined section. What happens? How does it change from being this simple normal stress case to the more general setting if I have an inclined section? So let's just do some geometry to help us move in that direction. It's really just some basic geometry. Let's say we have a cut like that, and just build some triangles here. So we have triangle there, and we have an angle, let's say theta there, and then if we were to look at the distribution of the internal force, it should look something like this, okay, where this uniformly distributed internal force, the resultant force should again always be balanced by statics. It should be equal, the resultant force should be equal to P. But now we're on this inclined section. The cross section for this guy, right, is going to be what we call A1. And A1, the cross section of an inclined section, the cross-sectional area of an inclined section is different than the area of a vertical cross section. It should be a little bigger, right? So this should be bigger than what we were using before. Okay. Okay, so let's take a look now at a little element. If we cut a little element out here, okay, and zoom in on it, we end up with an element that looks something like this. Okay, it's got an angle theta. We have our resultant force, magnitude P. And then if we take this resultant force here, which is a vector, and cut it into and decompose it into two vectors that are perpendicular to one another, this one we'll call N, and this one we'll call V. So this vector and this vector are equal to P, right? So these are the components of P, of the applied force, in the kind of the coordinate system, or the vectors that are normal and tangent to the cut plane. Okay, so if we look at a right triangle here, we put these vectors on a right triangle, then we end up with something like this, where we have our angle theta, and then this is going to be our vector p, this is going to be our vector n, and this will be our vector v. Okay, so that's how this decomposition works. Here's the geometry of that decomposition. And now we know that cosine of theta has to be equal to n over p, and sine of theta has to be equal to v over p, which means now that n is equal to p cosine of theta, and v is equal to p sine of theta. Okay, now this is valuable because now if I give you this load P and some angle theta for the cut, I can now tell you what the components of force are normal to the cut and tangential to the cut. Okay, and so now we're just one step away from some more insight into what stress is. Okay, so we have let me just bring down these equations so that we don't forget them. We have n is equal to p cos theta, and v is equal to p sine theta. And let's define sigma to be equal to n over a1. Let's define tau to be equal to minus v over a1. And I'll come back to this minus sign here in just a minute. Okay, and this is what we're going to call our normal stress, right? This is the stress that is normal, that's acting normal to our inclined cut. And this is what we call our shear stress, and it is the stress acting tangential to the cut. Now A1, this is the cross-sectional area of the cut. Okay, so let's just look at that for a minute. It's going to be, just again looking at our right triangle, A1 is just going to be A divided by cosine of theta. Okay. Now let's talk about this negative sign for a minute. If we draw a little picture of what we've got here, we have our inclined section, we have some, right, this is sigma, then we have tau, and we have kind of an embedded sign convention here. Notice that this force is going to tend to bend this guy into something that looks like that, right? This force is going to want to make a frowny face out of this bar, and we call that clockwise bending, and so that's a sign convention. Negative is what we call clockwise bending, and so we call this a negative shear stress because it produces this kind of a shape when it's applied. It's kind of bending the beam into this frowny face. Okay. If the stress was pointing in this direction, then it would be positive. Okay, so this is just a sign convention. That's a choice that we make, but that's the rationale behind why it's negative. Okay, so let's return to what we have here. Okay, we have A1 here, right? It goes in there and over there. Now let's plug everything together and come up with some nice new notation. So sigma theta, okay, so this is the normal stress for a particular cut at an angle theta. It's going to be equal to n over A1 plug everything in, right? Plug in the definitions for both n and a1, gives us p over a cosine squared theta, and tau theta is v over a1. It's going to be equal to minus p over a sine theta cosine theta. Okay, now we can use some trig identities, and I'd encourage you to take a look in the book to see how they do this simplification. It's just a detail that's not particularly important, but this isn't the final form that you'll normally see. They're going to apply some trig identities to these to further simplify the expressions so that we end up with the following. Sigma theta is sigma x over 2, 1 plus cosine 2 theta, and tau theta is minus theta x over 2 sine of 2 theta. And remember that sigma x is just p over a, right? So this is our standard definition of the normal stress. So given the normal stress, so what's nice about these equations now is these are very important equations. Okay? What's nice about them is if I give you kind of the normal stress on our standard vertical cut plane, and then I give you some inclination angle, then I can tell you what both components of stress will be, the normal and the shear, given those two parameters. Okay, so if I plot these equations, let me rewrite them just so we have them in front of us. I have this equation here is sigma x over 2, 1 plus cosine of 2 theta, and tau theta is sigma x over 2 minus sine of 2 theta. Let's plot these so that we can take a look at how normal and shear stress interact and how they depend on a given angle theta. And since these are just sines and cosines, it's very easy to plot these guys. Okay, so let's call this over here minus 90 degrees, minus 45 degrees. This will be 45 degrees and 90 degrees. Okay. So let's plot sigma theta first. So sigma theta is going to have its, see if theta is 0, it's going to be, so if the angle is 0, right, we're looking at this equation. If theta is 0, then we have cosine of 0, which is 1, so it's just sigma x. So there's sigma x up there. And then at pi over 2, it's going to be 0. So it's just a sine function that looks like this. This isn't a perfect plot. Okay, so this is the function sigma theta. Now if we look at this second guy at theta equals 0, this is going to be 0. So notice that when sigma x is at a maximum, right, when our normal stress is at a maximum, we have no shear stress. And that's the case that we first introduced in the class when we had a vertical cut. Then as the cut moves away from being vertical by a given angle theta, then these start to interact. normal and shear start to act at the same time. Something like this. Again, my drawing is poor here, but okay, so this is tau theta. Okay, and so now what's nice about these equations is you can very easily, given any angle theta, pick off what the components of the shear and normal stress are. Okay. And I would encourage you to learn maxes and mins, etc. Like different, it's good to know where the maximums are, where the minimums are, etc., etc. Let's just do a very simple equation. There's a simple problem, similar to what you'll find on the homework. How you put these into practice. It's very, very basic now. So we go get our bar. Okay. Let's load it up. Call that sigma x. Let's take some cut that. Okay. It's going to be our theta. Sigma x, the magnitude is minus 72.6 megapascals. Okay. All right, and then let's call this plane RS. So this we'll call plane RS. And so let's suppose that the compressive stress is 65 megapascals on plane RS. Okay. And we want to answer the question, what is tau theta? Okay, so this essentially here is sigma theta. So they've given us sigma theta, and we need to figure out tau theta. So the first thing we need to do is figure out what theta is from sigma theta. So step one is determine theta. Okay. So remember, sigma theta is sigma x cosine squared theta, which means that cosine squared theta is equal to sigma theta over sigma x. So we have both of these, right? So then we can just take the inverse cosine, and it's going to give us that theta is going to be the inverse cos of the square root of sigma theta over sigma x, which in this case is equal to about 18.9 degrees. Okay, so now we have theta, and now we can determine tau theta very simply because we have sigma x and theta, so we can just plug it right into the equation. So tau theta is equal to minus sigma x sine theta cosine theta, or the other, you can use trigonometries and use the other form if you'd like, it doesn't matter. And you plug in all the numbers because you have everything here, and you end up with, I think it's 27.2 megapascals. Okay, so in summary, this lecture is kind of introducing you to this idea that the stress, the behavior of the stress, depends on the orientation of a cut plane. That's a very fundamental idea. So as the cut plane rotates from theta all the way around 360 degrees, the normal stress and the shear stress, their magnitudes vary. And this is a kind of the precursor to this much more general idea of plane stress that we're working towards in the class. So the problems are quite simple in your homework, but this idea, I would encourage you to make sure you understand the geometry and kind of the steps of the derivation that I went through in the lecture so that you really understand the backbone of where we're headed with stress.